Okay, welcome back everyone. In this video we're going to be talking a little bit about some of the properties and characteristics of waves. So we're going to start with a definition, and so there's a lot of common perceptions of waves just kind of that you might already know about, but what we're going to focus on for a wave is a regular periodic disturbance. And this is a disturbance that occurs in both time and space. And most importantly, it transmits energy. So these are all kind of fitting together to give us an idea of what a wave is. It's a regular periodic disturbance in time and space that transmits energy. So most periodic waves are going to vary with a sine or cosine. And you might have heard of that in geometry or in trig or whatever math you're taking. And one way to think about this is that these are functions of time and space. And if that seems kind of weird, well, let me show you a quick applet. So this is a wave on a string. Okay, and what I can do first of all is I can just show you one pulse going by, and let me do that one more time. Okay, let me slow that down a little bit. I guess that was a little bit too slow. Okay. Well, in any case, what I want to show you about a periodic disturbance is if I make this wheel kind of turn around in a circle, then this green dot here, which is attached to the circle, is going to actually oscillate like this. And so you can see that something moving back and forth creates kind of a sinusoidal pattern. Okay? And this is a sinusoidal pattern both in time and in space. And this plot that we can see right here is only showing us the space aspect. Okay, so another thing that I want to point out for a wave is that the energy is transferred from one end to the other, but not the individual particles that make up the wave. So if you think about this as lots of little objects that are maybe attached by springs, let me pause this for a second. Keep your eye on this green guy right here, and let me go step by step and look at what happens. So I know it's kind of hard to see, but that green guy is not moving left to right, it's just moving up and down. And so what's happening is that the particles to its left and right are pulling it down or up because of spring forces or other forces that we can discuss a little bit later. But the basic idea is that the wave propagates or moves forward, whereas the particles vibrate up and down. And that's a pretty common characteristic of lots of types of waves. Okay, so now let's talk about some of the characteristics or properties. So we'll start with amplitude, and the amplitude of a wave has the symbol A, and it's measured in meters. So I'll put all of them like this, with the thing that you would put in an equation, the variable is going to come first and the unit will be next. Okay, so this is the magnitude of the maximum displacement, and displacement can be positive or negative, from equilibrium. And if I go back to my applet here, you can see that equilibrium is this dotted line that goes across. So then the amplitude would be kind of the height of this guy. And so if I, whoops, let me turn that amplitude down a little bit, and so you can see that the height is a lot less. Okay? Alright, so one thing to keep in mind is that the energy transported by the wave is proportional to a squared. And we'll talk a little bit more about this in a moment. And actually, when we get to discussing simple harmonic motion, we'll say more about this. Okay, next is the wavelength. And you probably already know this from chemistry. Wavelength we're going to measure with the Greek letter lambda, and it's measured in meters. Okay, and this is the distance between two successive parts of a wave. So if I have a wave that looks kind of like so, my drawing skills are okay today, I could go from a crest to a crest. That would be a wavelength. If I kept going with it, I could go from a trough to a trough. That would be a wavelength. And if I picked some random point and another random point the next time it came around, that would also be a wavelength. One thing you want to be careful of is that going from here to here is not a wavelength. That's actually half a wavelength. And make sure that you understand why. Because on the left, it's like where the wave is starting to go up, but on the right, it's where it's coming down. So that's not a full wavelength. We'd have to go all the way to here where it's coming back up again to get a full wavelength. Okay. Next, we can talk about the frequency. And the frequency is F, although in chemistry you sometimes use the Greek letter nu, and it's measured in hertz, which is the same thing as 1/seconds, and it's basically the number of cycles, or if you like, you could think about the number of waves per second. And we'll talk a lot more about frequency. The period, the capital T, is measured in seconds, and this is the time for one complete waveform to pass by a given point. And one thing that we can do is say that the period and the frequency are inverse of each other, and that makes sense if you look at the units. 1/seconds and seconds. And the period is the time for one wave, and the frequency is the number of waves per unit time. So they're inverse of each other. Okay, next we've got the wave speed. And this is just like any other speed. We'll write it with a V and measure it in meters per second. And that's basically just the speed of the wave. And there's two ways to calculate it. You can do the wavelength over the period, or you can do the wavelength times the frequency. And so we'll talk about the wave speeds for various waves. Okay? And that's actually going to be a huge part of the wave project that we do later on. And finally, let's talk about the two major types of waves. We have transverse and longitudinal. And it all has to do with what the wave is doing, the particles that sort of compose the wave compared to the direction the wave travels. So what I mean by that is, in a transverse wave, the particles of the medium vibrate at a right angle, so I'll just say it perpendicular to the wave motion. And transverse waves pretty much just go through solids. And we'll talk a little bit more about that later. As an example, this is a transverse wave. Each of the green dots are moving up and down, but the wave is moving left and right. Okay, So the opposite of that is a longitudinal, where the particles of the medium they vibrate parallel to the wave motion. So these are also called compressional waves. And we're going to see a good example of this when we do our Slinky lab in class. So keep that in mind. Okay, another good example of longitudinal is sound waves. Alright, that's pretty much all I wanted to say for now. I just want to give you an introduction to some of the characteristics of waves.